right, we're going to put everything together on page 152. We're going to start with the backwards method. We're going to do the residual analysis method for the polynomial model. We're then going to do a partial F test and put that together with it. And then finally write out the final model and interpret it. So we're going to try to put it all together for polynomial regression this. So it's going to go a little quicker, but I think you can follow it. Okay, so we're trying to put all together the polynomial regression together. So from your course pack, you can see that there on page 152, we're going to do these steps. Apply the backwards method, do a residual analysis, conduct a partial F test, and then write out the final model and interpret it. So let's go ahead and do that. Let's first of all do the backwards method. So here we're starting off with our response variable as being log ratio, and our predictors are time squared, days, weight, loss, tumor, treatment, and female. We're just doing an exploratory amount to see which ones we should keep in our model. Well, if you look at this, not all of these are above or below 0.10, so it looks like I should get rid of days. And so if I get rid of days, then I look at the next one, and it looks like I should get rid of females. And then the next one, the highest one is 0.390, so I should get rid of that one. And then finally 0.378 tumor. So hey, I must be getting good, I must be done. But lo and behold, once I get rid of that, another one pops up, the loss. So I have to get rid of that one. And now lo and behold, at least according to the backwards method, then this is going to be my model. The log ratio will be this part right here. So I'd write that in for part A. And the predictors that survive were time squared, and treatment. I don't know if you remember when we did the original residual analysis a while ago, there seemed to be some sort of curved linear relationship when we looked at time. So that's maybe not as surprising here that we got time squared. Now let's go ahead and do a residual analysis here. So I'm going to go ahead and do this part again. Let me show you a little trick that I forgot about to show you before. So I'm going to go to stat, regression, and regression. To fit the regression model, I've got the log ratio there, and I want time squared. Now, I want to make sure that I get my fits and my residuals, because I need to work with those. And then there's something else that I'll be able to do here that, and I want the graphs here, and my model's okay. I don't need anything more than these parts right here. So for the graphs here, I'm going to do the 4 and 1, but then down here I can put the residuals versus the variables. So I'm going to put time squared, and treatment, so for when I do the residual analysis. So again, what I've done is that, well, I went ahead and okay, but when I did the graphs, I went to that part. So I've got this part, so let's do the residual analysis. Remember, for assumptions, I need to check some that follow from the error random variable. So I need to make sure that my residuals are randomly distributed. So if I do the normal probability plot here of probability plot, and I want a single one, and I need to graph the residuals. And if I did that okay, I need to check to make sure. And now again, the p-value is bigger than 0.1 or 0.01, so I'm okay. Take a look at it. I have one outlier here that might cause me a little alarm, but I think I can assume that the residual normally distributed. I'm a little concerned that there's a pattern here, but nevertheless, that I'm okay. Let's do a matrix plot of the log ratio versus each. Of the plots there. Here's my probability plot. And here's my plot there that I don't want. Sorry about that. What I want to do is use the regression analysis of the scatter plots versus each one. So that's not the one I want. So That's a little extra bonus information that we have there. So I want the matrix plot. I want each y versus each x. I'm going to do OK. Instead of the log ratio, I want the residuals versus each of the 3 x variables. So if I go ahead and look at that, then I can see, are they roughly scattered about 0? Yeah, there's like a drift, but you know, these are sort of like categorical data, so it's not really as helpful to kind of see that. And so I'm maybe a little concerned, but I'm not concerned very much. So the model's assumptions appear okay. So now let's go ahead and do a partial F test, okay? So the partial F test is, you know, I've gotten rid of days, females, tumor loss, and weight. So if I do this verbally, I'm going to say the null hypothesis that the predictors, days, female, tumors, loss, and weight do not help explain the response variable y. And the alternative, at least one of those predictors does help to explain the response y. If you kind of like more symbols, you can say the reduced model. The model is beta naught plus beta time, x1 plus beta time x squared, x1 squared, and so forth. That's a reduced model. There's only 3 predictors. And the full model, I had all 8 of them. And I'm going to use the partial F statistic. I'm going to use this over again, so just kind of, you know, keep in the back of your mind. Your sum of squares there is reduced minus sum of squared error full. Degrees of freedom reduced minus degrees of freedom full divided by the mean squared error is full. So that's one thing about Minitab. If you come in here on the left, this is my regression analysis of the time, and I need to look at and find out the sum of squared error full. I'm sorry, this is the reduced because I have fewer variables, and that's 9.828. And I can go back to where I started from and look at my model summary that my sum of squares errors here was 8.52254, and then here's my adjusted mean squared error. So if I go ahead and look at what my F statistics will be, I need the sum of squares errors reduced minus the sum of squares errors full. So I've got 9.828 and 30 from my reduced model, and this is back here. We've got the 9.828, my degrees of freedom is full. That's my blue. And if I go up to my red for the full, for the full model, I can see that my degrees of freedom is 25, my SSE is 8.2454, and my mean squared error is 0.3302. And so I can plug those numbers in. Make sure that you divide this big numerator before you divide, because there's a lot of times you can make a calculator error. Notice that this denominator is 5. That's just the number of predictor variables we got rid of. So you may not want to subtract. You just kind of think of, well, I got rid of 5, so I'm going to put 5 there. And so we get a 0.934. Notice that my degrees of freedom corresponds to this difference, which is 5, the number of predictors I got to get rid of. And the denominator corresponds my degrees of freedom for the full, and that one was the 25. Okay, so there's the 25 right there. And so I can continue on. My denominator is, I go ahead and find this out. My p-value is 0.4646. That is greater than 0.05, so we fail to reject the null hypothesis. The data do not give evidence the other predictor variables are needed beyond time, time squared, and treatment. So that's my that's part C of page 152. And then I can write out the final model and interpret it. And it seems to be that time and time squared, a quadratic function of time plus the treatment, does help explain the log ratio response. Now, what do we can conclude about the BD treatment? Well, in this case, we look at the coefficient as 0.762 and the p-value is 0.01. So we should say that the treatment does make a difference in the log ratio. As a matter of fact, I went ahead and calculated the confidence interval. Remember, you take your estimate plus or minus your multiplier times the standard error. My degrees of freedom is 30, and my estimate was 0.762, and my standard error is 0.196. We can just kind of double check that. There's my degrees of freedom is 30, and there's my treatment coefficient. That's my estimate, and then there's my standard error. And so I can put that all together, and between 0.362 and 1.62 in all the variables. So it does tend to increase the response variable. Matter of fact, maybe I should have done a confidence interval where this is just straight or greater than 0. But nevertheless, it does appear to increase the treatment. Now, let's look at something very interesting at number 5. Do a regression with only the predictor's time and treatment. So this is number 5. So let's kind of go back and take a look at this one. If I only do a regression analysis with time and treatment, notice what my coefficient is. It's still about the same, 0.74. But if I look at my p-value then, it's 0.077. So I would reject that this has any effect on it. And this is the part of the statistics that you have to take in all the information. There's usually not a black and white answer. There's some gray in there, and you have to take a look at it. So in this case, treatment does appear to have an effect, but only if we have the model where we include time squared. So that's the that's the information that I wanted to show you, sort of putting it all together. And let me see if I can show myself because I need to say goodbye. Okay, so there we have put it all together. What we did was, I think it was black that we started, we did the backwards elimination method. We did a residual analysis to see if our model fit. We did a partial F test to determine or not whether our model is appropriate, or at least what kind of conclusions we can do. And then finally, we did some looking at the final model and interpreting. So we put it all together with everything that, a lot of things we've learned previously in this time after spring break. And these are things that we'll keep doing. Again, the idea is that we're taking our basic understanding of the linear model and extending it to other ideas. And really, it's becoming quite powerful. And here, this is BD treatment for in terms of rats. Maybe someday we can make some discoveries that can also do some helpful things in the world.